Hello, hello. I'm sorry, something wrong happened with the existing stream, so I had to end it and create a new one. I know it's confusing, but this is first time for me, so I'll pay more attention next time and try to figure this stuff out. I hope it makes sense what I'm trying to do. So I'll still wait for a couple of minutes to see if anyone is joining in. By the way, just feel free to let me know if you are able to hear me properly or not. Because again, as mentioned, this is my first time, so I'm pretty pretty confused on how will it behave. But that is first time for everything. So okay, so purpose of this stream is to make sure that I am able to basically check what is happening around like software industry and just give a quick introduction about myself and then talk about system design basically. So that system design is a very popular topic currently. It is highly relevant because without system design I don't think we would have any kind of infrastructure or technical infrastructure that we have today. So it's pretty evident why do we need it. Question is how do we learn it, because it's not something that you can mug up in a day or a week. It takes months and years to come up with the solutions, to understand all the constraints, why something works the way it does, why something doesn't work. So it took me a lot of time and I'm still learning continuously. This is an ongoing journey, but I want to make it interactive. So I want to make it like learn and then I teach. And Einstein once said that you only know that you have learned something properly if you can teach it in simplest manner. So that is the expectation here. Let me just quickly go back and check the stream if someone is joining in. I hope people are able to see it. If not, we will still just go ahead and live stream this one. Maybe in the future we can sort of have a better connection and a better stream. We'll see. Okay, so let's just start streaming. That why do we need system design first of all? So before that, first let's try to understand that what is the concept of any single I would say application. Suppose what anything in your mobile phone or any website simply does it is that it takes some sort of input. Based on the input it does some sort of processing. It could be anything. It could be like a payment gateway, or it could be something as simple as like uploading a picture, or anything it could be. But basically what it does is it takes some input from either a user, business, company, other machine, anything like that. It does some processing. It sometimes or most of the times it needs to store a bunch of things. It needs to dig deeper into its database. It needs to, I would say, call some other complex systems, do all of these things, right? These things are tend to be typically hidden from the original user, and then whatever the solution they have done after processing everything, they need to return some sort of output. And this is the common functionality of any application. Now this can be simple, complex. It could be an application such as Amazon, which is a huge website that has millions of products, millions of images, and you can do bunch of things, like you can see things, you can buy things, you can put your products to sell, you can do all sorts of things. Basically everything is done in the Amazon, and it's completely away from your eyes. All you can see is that you can provide the input saying that, hey, I want to buy this thing, I am willing to pay for it, and then it does all the processing. It takes your address, whatnot, and then simply it returns you the confirmation saying that, yeah, you already bought this product, we already received the money, or we will receive the money in a couple of days, and you should have the product shipped to you in this many days or this many hours. But behind the scenes they do huge amounts of computation that we are completely unaware of, and this is what we need to learn. So let's go back now. We started on a very big node, but let's just go back. Okay, so we know what an application does. Now for all the focuses of this initial introduction, we are going to consider that suppose we have a hugely popular application that simply does, or that simply says that I love teddy bear. So I love TB. Okay, I love teddy bear. This is all it does. This is the entire application that it does. Whenever you call it, so whenever you use the URL that you have, typically we have URL like www.facebook.com or something like that. Suppose for this one we have www.teddybear.com, and whenever we call this teddybear.com, it is going to say I love teddy bear, and this is what it returns as the output. Now you would say that yeah, this is a pretty simple application, there are no issues with this one. So why do we need system design, or why things become so complicated when it's so simple in nature? The question is, okay, this you can actually implement in your own computer as well. So suppose you initially start with your own computer. On your computer you have created a program that simply prints out I love teddy bear, and whenever you call this program, all it does is it takes the input that hey, someone is calling me, it returns as the output that I love teddy bear. Okay, I love TB, and this is pretty simple. Now you would say that okay, let me go ahead and publish this application, and still at this point you are using your home laptop or your home device as the sort of place where this I love teddy bear service runs. So you go ahead on the internet, you create your own URL that I love tb.com, and you publish it. Then you go on Facebook, you go to your friends, you start talking about it, that hey, I have created this amazing application that whenever you call this URL, it is going to print that I love teddy bear, and this works beautifully. You are just sleeping in your sleep, you don't know what happened. Someone, maybe some guy, Mr. Beast, tweeted out that this is the most amazing website in the world, or people just found out randomly, and this became a huge trend that this website is now the #1 website in your in the entire world, and every single person is trying to call this website. What is immediately going to happen? Because currently, remember, your application was still running on your home device, on your laptop, computer, PC, whatever. Before, your PC was able to, let's say, arbitrarily handle around like 50,000 requests per, I would say, per hour, because that's reasonable. Say it had the capacity to take care of 50,000. Let me just put down 60,000. So per hour 60,000, maybe 1,000 requests per minute, and this is a reasonable thing that a decent laptop can handle. This was able to handle it quite smoothly, but now what happened is that suddenly you post it on the website, and now let's say 10 million people are trying to contact your website every single second. Immediately what is going to happen is, first of all, your application is going to completely stop working. Why? Because your home device is not capable enough to take care of 1 million applications or 1 million requests as an input per second. Okay, so now what comes to your mind? Your mind suddenly goes, hey, I need a better computer. Okay, that is first thing. Say you also found a better computer, you find one big giant computer that is capable to handle 10 million requests per second as well. You put this computer at your home. Again, your application that was previously running on your home device, now it is running on this quantum computer. Okay, still what would happen when 1 million people tried to access this app website? Again, despite your computer being able to handle this, still this is going to crash, and people won't be able to use your application. Why? Because these many people are simply block off the network. And what all of these things means, we will understand it in a simple terms. But imagine that suppose there is a bank, there is a huge bank in the world, and this bank is giving out free loans. So who doesn't like free money, right? It's giving out free loans. It said that it is going to give 10,000 free loans every single minute, and people are able to get it. Though bank has all the money, bank is a huge bank, people are able to get the money, but what would happen is the way to reach to a bank is just a simple one lane road. Now what would happen is that there are probably millions of people lining up to get the free money, and they all have to go through this simple short path to get to the bank. Even though bank is completely capable, still only like maybe very few people would be able to get in, despite millions of people being or waiting to get in, because the road were too narrow. Same thing is going to happen in your system, that despite your computer being the most powerful computer that is able to handle I love Teddy traffic, it's still going to break because the people are trying to get in through a very narrow bandwidth of network. So first issue we found was that your original home device was not capable enough. Suppose you upgraded your home device, your quantum computer, still your network was not good enough. Now say you take care of all of these things. Currently you have the website iloveteddy.com, and this website, the quantum computer is doing wonders. You also put down huge networking lanes in front of it that is able to take care of all of these things, and you try to say that okay, now 10 million people come on and get show your love for the teddy bear. Still there are going to be issues present, or there are going to issues come in the future, and you won't be able to sleep, that is for sure. Why? Because suppose 10 million people, they start accessing this application, it works as expected. What would happen if suppose the city you are currently living in, suddenly the power goes down? If the power goes down, your quantum computer fails. 10 million people are going to be angry because they are not able to see their love for the teddy bear. And same way, suppose rather than now your city is going now you say that okay, I'm going to do something better. What is the better? You are going to put an inverter that is going to take care of the power failure scenario. Suppose the inverter also failed after some time, it ran out of gas, it ran out of electricity, again your quantum computer failed. So these are all band-aid solutions that are in some way, shape or form leading you to have bunch of issues that you are not able to resolve, despite you having the best cutting edge technology possible. You are using the NASA computers, you are using probably Tesla networking routes, all of the cool things, you are having the best internet possible. Still you would wonder that why so many people wants to use my application. I'm using all the cutting edge best in the market things, still I'm not able to still I'm not able to come up with the optimal solution, because you are relying on single point of solutions. Here your quantum computer is a single point of solution that could fail at any moment, that you haven't prepared for. Next thing, there is networking paths that could fail at any moment that you haven't prepared for. These are just couple of issues I mentioned. There can be bunch of issues. Suppose there are some hackers present and they wants to break this website. They have bunch of different ways of doing it. They have suppose DDoS attacks. So what DDoS attacks is that it is going to start creating these fake accounts, and it will start sending out, rather than 10 million, let's say it starts sending out 1 billion. So that is 100 times of the payload that you are able to handle. And now even your quantum computer is starts to fail. So again your website goes down, because you don't take care of this scenario. Now apart from this, say these bad actors, they somehow try to get access to the source code and try to change a few things, like rather than I love teddy bear, they change it to I hate teddy bear. Now what would happen is that every single user, they are going to feel sad because they did not got what they wanted. There has been some manipulation happening in the system. All of these things are basically the things you need to consider if you are building any application, and this is where software architecture or system design, these all things come into play. And I'm going to go over every single thing. By the way, hey Ali, hey Depression plus plus, Thanks a lot for joining in and sending out the message. Now let's just go back to the question. So that is why we need software architecture, because there are a lot of things that can happen. And again, my sincere apologies for my handwriting, they are pretty bad, but I will try to improve upon them, but it is what it is at the moment. So now let's just again go back to the software architecture. First we will try to see that what are some of the key important things we need to consider for any application. We already know that applications can have a bunch of different issues. Now every single time using a quantum computer is not feasible financially or logically. So what could be the other solution? Suppose you expect that this is your application and it suddenly starts receiving bunch of different traffic. How you are going to handle it? So one possible solution is that previously when you are using just your home device, rather than using one home device, you start using two home devices. Apart from using two home devices, you start using three home devices, and you keep on adding these things. That what it does is that whenever some payload comes in, certain amount of traffic goes to this first device, certain amount of traffic goes to the second device, and certain amount of traffic goes to the third device. So ideally you basically distribute the load in some fashion, and you are going to have some mechanism in between to do that. So we will typically call a load balancer for that. So what it does is that takes the load that comes in and tries to distribute on the different servers so it can be handled efficiently. Now just the moment you are learning about these things, I'm also going on different concepts as well. So this first concept that you see, where initially we only had one single home device or one single laptop that was running the server, because the load increased, we started using bunch of more servers. So what we did is we increased the number of servers, so we scaled out our servers. But this scaling is actually done in the horizontal manner. Why horizontal manner? Because we started adding more and more servers, so we started increasing the capacity of the application, but we did it in a horizontal manner. And same way, suppose rather than using all of these three home devices, we decided that we found a giant quantum computer that is able to do all of these things, and we are able to feasibly handle it. If we would have implemented this, what we would have done is that previously we only had one home device. Now we have a huge quantum computer that is much more capable of handling the traffic. So this is called vertical scaling. So these are two important concepts on any system design that comes to your mind, and I just explain you their meanings, that this would be vertical scaling. Now let's just go back. Okay, currently we are not considering the vertical scaling at the moment because it's very expensive, and also there is a possibility of single point of failure. So typically what we would do is we would focus more on horizontal scaling for any single system design, because that is more feasible. But even during the horizontal scaling, you can still do vertical scaling by increasing the capacity of any single application or any single server. So that is why we will try to beef up the softwares that runs our system, but still we would have more systems running our softwares. I hope that is, I know that is poetic, but still it is accurate. So this is one way to handle that, how we are going to deal with all of these things. Now I mentioned that we are going to typically use a load balancer. There can also be an API gateway. There can also be a bunch of different things that we can use to take care of this. But let me not shout out words before explaining them. So first let's understand what an API is. Okay, API is a very important concept. Now try to imagine a scenario where you are sitting inside a restaurant. Now inside a restaurant, typically we know that there is inside a restaurant there are a bunch of different tables where people are sitting and ordering food and eating bunch of different things. Now inside the restaurant there is typically a front staff, then there is also a menu, and then there are I would say just like music, design, all of these things. Those things are there to keep up the ambience, to make things look good, look beautiful, and that is typically referred as the front end. in terms of the website term, because what front end does is that even if you take out any website, say if you just take out Instagram, now Instagram is typically made out of bunch of code, but you don't know what that code is. All you are concerned about is that all the stories or all the photos your friends are uploading and you are seeing it. So what you see in the front, that is typically called the front end side of the application. Same way in the restaurant, all the things that you see that are just there to be attractive, they are typically the front end portion of it. Also in the restaurant, we all know that there is a kitchen that takes care of all of these things, and kitchens are not tend to be as fancy or as good looking or as beautiful as the typical restaurant is. But in the kitchens there are a bunch of different people who are working tirelessly to make food, make it look good, prepare it, get the menu, start doing the preparation, depending on the menu, start filling up the order, and then call the whoever, like waiter or waitress who gave the order, provide them the food item, that hey, this food item has been prepared. So this kitchen would be referred to as the backend, and this is what the backend is for any single application as well. That is bunch of different code, servers, applications that run your software, data. There can be bunch of things, but those comes typically on the behind the scenes kind of a way, and that is referred as a backend. So that would be in the backend side. Now how every single thing is going to be coordinated in the restaurant, that would be coordinated by the person or by the waiter or waitresses. So this is going to be referred as the APIs, because what they would do is they would simply they would reach out to the people, they would reach out to the customer, first of all give them the menu saying that hey sir, this is what our specialty is, these are the things we provide. If you are interested, feel free to reach out to us and let us know what you want, what do you want for food. So that is one person or one waiter or one API that took the order. There could be another person or another waiter reaching out saying that hey, you want some water, or you want some bread, or you want something as a starter that is complimentary from the restaurant side. Again, another API call was made to the customer. Then customer said that okay, I want let's say salad. Okay, so customer provided the input that customer wants the salad. Now what the waiter is going to do is waiter is going to take this, note down this order, that this table number wants a salad. It is going to go back to the kitchen. In the kitchen, there would be a person assigned who is going to work, who would be working on that, which table number had which order, and that person would order the chef, or in this case chef, sous chef, depending on the complexity of order. He would say that they need one salad for table number 34, and this the chef would then start making that. Once chef makes it, it is going to again say that okay, this order is now ready. That person is again going to call the waiter, and then waiter is going to bring salad back to the customer. This is an example of an entire call. So typically this is how the combination of APIs with various things makes the software do things on their own. So in this example, again going back, waiter was actually the APIs, restaurant was the front end, and kitchen was the back end. All the person in between, they could be like mediators, gateways. They are there to make sure that correct order gets passed on to the correct person. So there are additional checks. There could also be one person in between in the kitchen to make sure that that person distributes the load correctly amongst all the chefs. So one chef is not completely bombarded with bunch of different calls, and meanwhile all the other chefs, they just go out and do gossiping. So that person we would typically refer to as a person who is distributing the load correctly, properly. So that can be like a load balancer. So these are the things that are typically the system design lingo that you need to understand. Now there are few pretty important stuff, and those important stuff are the trade-offs. Now trade-offs, we are going to start understanding them later out when we go deeper into system design. But now for the today's session, my concept was to explain you the brief concept on why do we need system design. So now again, let's just go back to our question, and now we will start designing the I Love Teddy system. Okay, so initially we started I Love Teddy system with a simple home device, and now in this home device there was only one person, myself, who was making these calls, and my home device was able to compute correctly that I need to print out I Love Teddy, and it gave me the output as expected. So I was pretty happy. Now because I was happy, I went out to my friends and said that, hey, you should start calling my website that I have published on the internet right now, because previously this I was running locally, and even the local run and the internet run tends to be the same things in practice, sorry, in theory, but in practice you need to be okay, some guy said it can be a dentist also. Okay, yeah, that's good. Okay, now let me just go back. So in practice it needs to be, it can be different things typically. So say you, now I have this website completely published on the internet, and still it is using my home device. Now because bunch of different more people started calling this website, my website would work for some people. So these are all the people it worked for. It would occasionally fail for some people. So then I would start instigating, and I started to realize that my home computer was not capable enough. So rather than using this home device, I beefed up my scale and I get a bigger home device that was able to do much more things. It had better RAM, better functionality, and now I started to again repeat the same process. In this case, more people were able to access the service easily, but still I was not expecting the scale to go such high that entire America started using it. When the entire America started using it, even the beefed up version started failing. So what was the next thing I did? I bought bunch of beefed up computers, connected them with each other, and they all started to sync up. But now from time to time what happened is that, first of all, these two servers, they were getting most of the load and that was working fine, but the other servers, they would rarely get any load, and though they had the capacity, and because only these two servers, they were mostly saturated, I would often see some calls again failing. So that is again a bad thing. Because this is a bad thing, I started to implement a load balancing system in between that that would distribute the load equally amongst all of these servers I had. Also at the same time, what I did is I went ahead, did something smarter, that I said that, hey, I'm going to have all of these 5 different servers or 6 different servers available to me in case the load goes significantly higher and I run out of the space amongst all of these things. So I would keep on automatically adding new server into my system. They would be able to join in amongst these blue clans. So among these things would join in, and one would be redacted from the available servers, and also at the same time load balancer would be notified that, hey, there is one more system that needs to do something better. So again, cool things would start happening. That I noticed that during the afternoon period, my load was going significantly higher. So all of these things, they were automatically assigning new systems and they were working fine. And some systems, when during the night time, when the load went lower, some of the already assigned softwares, I released them and even released from my load balancer and also kept them on the side, so that reduced my overall cost, and also at the same time I was able to save some money. Now this is called automated scaling, because automatically or dynamically I was able to allocate some resources in the backend, and also I was able to get rid of some resources in the backend. So this is also a very important and critical concept. Now again, going back to our example, now these things are working fine as expected. There are no issues with this one. I did the most I could. The application is quite simple. It simply prints I love teddy bear. Now again, what happened is that my city lost power. Because my city lost power, immediately all of these things, all of my infrastructure, they simply collapsed in a second. And now my application is no longer feasible. Though people are calling it from all over the world, they're not getting any answer. That's a huge fault. Despite having inverter and whatnot, all of those things also ran out of gas. So now my system has stopped working. What should I do at this moment? Well, lucky for me, I got a little bit smarter. How smarter? Initially, this is my application. This is the entire structure I mentioned over here. Okay, this, let's say this is the entire structure. I would call it the infrastructure 1 that I had running for my application. Now at the same time, I realized that something like a power failure or something catastrophic could happen in my city. So I created the exact replica of this infrastructure and put it somewhere on the other side of country, or on the other province, or let's say even like 300 miles away from my city. So what happened is my city got lost power, it collapsed completely. Now I have this new city that works as expected, and that is still able to take care of my application. And I actually put an automated check. So what automated check was doing is that if initially I was calling my city 1 infrastructure, but the moment city 1 infrastructure collapse, instead of calling city 1, I would simply make a call asking that, hey, are you up now? Are you okay now? Are you able to take input requests now? If it can, awesome. If it cannot, I'll just get rid of it. I'll start calling this 300 mile further city. So I know 300 miles, that this is going to induce some latency because it takes time to make the call and get the call back in the answer. But still, at least all of my millions of followers, though they would be getting the result in some small time, they would still be able to make sense of it. So this is one cool stuff I have been able to implement. Now what I did is, initially I had a single point failure, that was my city. Now I included one more city. So now what I did is that I increased the ability to take care of the fault in my system. Why? Because currently city 1 was working perfectly fine, but something faulty happened and city 1 infrastructure completely stopped working. So in the previous example, I had no ability to back up, rather than to keep calling electricity guys that, hey, my application is completely dependent on this, can you please fix that? Now I have this another infrastructure that is completely ready for me to work, and now it is able to take care of my load. So this is how fault tolerance works, that my city or my infrastructure is now more fault tolerant, because it is able to tolerate that if one city goes down, let's say both the cities go down, again, this is the maximum fault tolerance I had. But I became even smarter, and in the next state, or inside somewhere in California, I had another set of these two city-like structures present, and when both of these cities failed, I shifted my traffic from California to my current city, New York, let's say for an example, and then things started working. So this is how this is how I made my system even better. Now say something even worse, catastrophic happens, earthquake happens, alien invasion happens, and entire America loses its power. Then now the maximum fault tolerance my system had was for both the states, but I just say that entire America loses its power. What would happen? Well, I even got smarter. I had one more application located in Canada that was still able to support my application, and now my application was much better in terms of fault tolerance. So now let's just take a step back. What we initially did is, first we only had one server. There was a single point failure or a single server. Then in the same sort of vicinity or same area, we had two identical servers running. So I made a geo-redundant server or geo-redundant infrastructure for my application, or sorry, locally redundant infrastructure, because this was still a similarly local area. Now after this, I decided to have one more infrastructure in New York and second infrastructure in California. So this time I made like a geo-redundant infrastructure, and later on I had one server or two servers in America, and I had two servers in Canada. And this is even better. This is even, I would say, continental redundant infrastructure. So this increased my fault tolerance significantly better. Now the question is, which one is good? The single point is good, the locally redundant is good, the geo redundant is good, the continental redundant is good. It's all of these are only be as good as the scenario it demands. That is where the trade-offs comes in, that depending on your situation you need to make sure that which level of fault tolerance you need. It could be possible that your application simply does a very simple thing, and even if that thing is not done, it doesn't matter. So you can have a single server keep on running. Like, I wouldn't recommend single server ever doing anything. At least I would say have two, but still single one could be worth it. But if even if it's something like less critical, you can still have locally redundant. You can still, or if it's something a little bit more important, you could have a geo redundant, like one in New York, one in California, maybe some one in Florida, whatnot. So but the moment you start increasing these things, you would also start increasing the cost. So cost is also a factor, then availability is also a factor. Remember, one wise person, sometimes that person told me that there are typically three things or three circle of impacts. One is a good, one is fast, and the third one is cheap. And if you want all three, it doesn't exist. So either you can have good and fast, or you could have good and cheap, or you could have fast and cheap, but all three are never going to be possible. Some way, shape or form, you would either have to pay more or compromise. So that is where the trade-offs. And if you think that cost is not an issue, well, handling a single data structure could be something like $4 to $10 million, depending on how complex this server is. In a simple terms, like this is, I'm not even talking about like these ultra megatech sophisticated servers. I'm just talking about some simple infrastructure. This can be this much expensive. So imagine if you say that I want redundancy in city, I want redundancy in all the cities, I want redundancy in all the states, all the provinces, and also all the countries, how expensive it is going to be. So some way, shape or form, you will have to identify that what are the requirements, what are the criticality, and then make the decisions. And that is why, again, I'm reiterating that why software design or system design is so important and so critical. Okay, now let's just go back to the example again. Now you made all of these things. Okay, you did horizontal scaling, you did vertical scaling. Now currently your application is properly fault tolerant. So it should be fault, oh man, I'm not able to write it. Okay, so now your application is fault tolerant, you took care of it. Your application is also properly load balanced, because you put the load balancer, you also put enough servers. It is dynamically scaled, so depending on the increase of traffic and decrease of traffic, it is able to take care of things. And it, at the same time, it is well distributed. This is the term I wanted to get to all along. Why distributed? Because we all know that we are using a cluster of structures or cluster of set of inputs that are able to take care of things that you wanted to do. Now initially, so far we were considering the scenario that all the people they are calling in, all of the traffic goes to a single data structure, single database until it fails. But what if we make something smarter? Because we already have a server located in New York, we already have a server located in California, and we already have a server located in Florida. So why don't we put all the people who are close to New York, call this New York server, all the people close to California, call this California server, and same way all the people close to Florida, call this Florida server. That way the latency is going to be reduced. And this is also a very important thing, that is to distribute the traffic based on the geography. So this we also implemented. Again, let me think if I'm missing something. So yeah, I think these are the things we have implemented so far. Okay, now our service seems to be working pretty fine. What we have is that every single time we have probably 1000 computers or 1000 vertically scaled and horizontally connected computers. They are located amongst all of these different geographies, and they are supporting our application quite easily. and we are able to do a bunch of things. Also, one more thing I mentioned initially, that the networking bandwidth, we also took care of the networking bandwidth as well. We increased the networking bandwidth, and same way, the load balancer that we have in the backside, we also have a load balancer in the front. Plus we also have like a API gateway kind of a thing in the front, and we are publishing all the services we have through our APIs, because our current service, I Love Teddy, got pretty busy, pretty popular. So we decided to publish one more service, but for that we did not create an entire new website. We simply use the same website, but we just created a new API, and that API is called I Love Babies, because who doesn't love babies? And this became popular. So at the same time, we created one more that is called I Love Dogs, and this also became popular. So previously we only started with one, now we have three. All three are being called by a bunch of different people, and depending on the input, that is being routed to a different service in the back. And we have thousands of virtually scaled and horizontally connected servers. These are all the things already present. Now, do you think we are done? Do you think everything is good with life? We are making millions of money, we are saving bunch of money because we have dynamically distributed load, and we identified the key priorities of where things are working or how it should work. Do you think we are good now? Well, think again. We are not good. Why we are not good? Because I just mentioned that we have 1000 server in just one location. Let's say we have 50 locations like that spread across entire America and Canada. So now we have probably like 50,000 computers that we are dealing with every single time, and that is going to take care of. So live stream. So right now my beautiful wife just came in, and she is going to listen in the system design. She already knows that what are the things happening, like she is the master of system designing. So okay, now going back to our example, suppose we have 50,000 computers that are doing all of these things, plus they are connected with bunch of different networking cables, and things are working smoothly at the moment. We know that every few weeks we have to update the software, we have to make some changes. Also some computers go down, also some computer lose their batteries, also some computer, there are bunch of issues happening with the computers all the time. For that, let's say you understand that you have, suppose 10,000 people, or let's just say 1,000 people. 10,000 people is just an overkill. You have 1,000 people who are consistently helping you out, do all of these things, maintain all of these things. And suppose we imagine that every day, I would say at least like one computer probably goes down once a year. We are just saying that one computer goes down once a year, nothing more than that. Every single day, if we have 50,000 computers or 50,000 servers that are running our things, at least 1,000 servers are going to go down, because one computer goes down every single day, probably in a year. Like one computer goes down in a year, so all 50,000 computers are going to go down eventually. There are 52 weeks, so typically every week probably like 1,000 computers need some sort of maintenance. That's a huge burden on these 1,000 peoples. Why? Because first of all, not all of these 50,000 computers are located at one place. They are geographically distributed on different places. So you are dealing with 1,000 people who are currently spread out across America and Canada, who is continuously taking care of all of these computers. Some are doing good, some are doing bad, some are doing worse. So even though we thought we had a near perfect distributed system, think again. Now we ran into the maintenance issue, and this is just the maintenance issue with the computer. What happens if the load balancer is outdated? You need to update the load balancer. What happens if the networking cables, they are stuck? You need to replace them. What happens if the internet standard change, and now you need to update the APIs? All of these maintenance, they are pretty costly because they are already running in production, and there are already existing customers. They are calling these services. They are expecting some results with fluidity, without any issues. So to maintain these things, it takes a lot of effort. That is why the companies such as like Facebook, Amazon, these companies, they make billions of dollars, because the services they do or they provide, it is not easy to provide in such a smooth manner. How have like how rarely have you seen Amazon services or Google or Microsoft goes down? Pretty rarely. And when they do, they make headlines, because so many people are calling them every single time, every single second. That is why they are so critical. So now again, let's just go back to our I Love Teddy service. This service, we did all the right things without worrying the cost, because we could have good, fast and cheap. We are eliminating the cost at the moment. We are finding the best thing possible. Still, this has been a headache for us. So how do we take care of this thing? We already initially started that how the distributed system works, how the distributed computing works, what are the benefits of using distributed computing, and then after having all of these benefits, what are the headaches for all of these things? Well, one thing that comes to mind, and that is to say someone who already has the existing structure, that hey, can you do this for me? And there is nothing wrong in asking for help, because you're anyways going to pay for the service. And that is why the cloud computing comes in. Cloud computing is that all of these infrastructures that we currently build, now all we need to do is just go and tell them that hey, we need these all these 5 services, and we are willing to pay for it. We are willing to go to a pay as you go model, and we need to use your service. And this is where the cloud computing shines. That is why if you see like AWS, Amazon, AWS or Azure or GCP, or all of these different cloud platforms, they are doing so good in the world right now, because they are directly taking all the headache from the service and they are putting it on themselves. So this is the key benefit of cloud computing. And I guess now my work break is over, so I'm just gonna go back, and I'll probably end the stream right now. I'll just wait for a couple of minutes to see if anyone has any questions in the chat. Feel free to provide the questions. Let me just okay. I hope I'm not too. Yeah, let me just go back to the YouTube control. Okay, cool. So I would wait a couple of more minutes to see. And also let me give the introduction about myself. So my name is Parth. I have been running this Destination FAANG channel for almost a year and a half now. So far I have solved a bunch of different lead code problems, and now I wanted to get started in the, I would say, system design phase, because it is pretty important. Now in terms of my experience, I've been working in IT for almost 7+ years. I used to work for a bank. It's the biggest bank in Canada, and I worked on like bunch of different microservices, different cloud environments. And after working on these cloud environments, I started working on I joined Nokia. So at Nokia, they had this huge existing application from 10 years ago. We started breaking the application and building the microservices kind of architecture, so that is smooth. And I haven't explained microservices yet, but I will explain them in the next upcoming sessions. Now and then last year I joined Microsoft. So currently at Microsoft, I'm working as a cloud solutions architect, and these are the things I have to take care of daily. Like there are a bunch of things that I don't know. I'm still learning, but I want to make this like learn as you go kind of an experience. So that is why I decided to start streaming, and I would probably stream like once or twice, or if 3 times a week. And yeah, so I hope things are good. And let me go back. So I'm going back to my job. See you again.